A very good evening to all the participants. We are delighted to welcome you to the day 5 of our online faculty development program. It is our honor to have with us Dr. Vinay Raj, who will be delivering today's insightful session. Before we proceed, let us take a moment to have a brief introduction of eminent speaker. Dr. Vinay Raj is currently serving as an assistant professor in the Department of Computer Applications at NIT Tiruchi. He obtained PhD in Computer Science and Engineering from NIT Warangal and MTech from BITS Pilani. His doctoral research focused on studies on migration of SQA-based applications to microservice architecture. He completed his postdoctoral fellowship at University College of Dublin, Ireland, and has a total of 8 years of professional experience, including 4 years of IT industry. Prior to joining to NIT Tiruchi, he worked as senior software engineer at Capgemini and software developer at TCS Hyderabad. Dr. Vinay Raj's research interests include software architectures, microservices, cloud computing, machine learning, and quantum computing. He is currently supervising one full-time and four part-time PhD scholars, including a few working in the domain of quantum computing. He has published several research papers in reputed international journals, including Elsevier and Springer publications. In recognition of his research contributions, he received the Young Researcher Award in 2021 from International Institute of Organized Research India. With his expertise and commitment to academic excellence, Dr. Vinay Raj continues to make significant contributions in the field of advanced computing and quantum technologies, inspiring young researchers to innovate and explore emerging frontier in computer science. Now, I take pleasure handing over the session to Dr. Vinay Raj. I request all the participants to remain attentive and actively participate to gain valuable insight from this informative session. Thank you.
Thank you so much, madam.
Thank you, sir.
Yeah, I hope my screen is visible.
Yes, sir.
Yes,
It's
sir.
visible.
Yes.
Okay, thank you. Good evening, all. I welcome you all to this top talk on quantum computing with ML algorithms, or in general, I will say quantum machine learning, right? So I hope you had good session last 4 days in this FDP. So before we go into what is QML, understanding the differences between classical computing and quantum or classical ML algorithms and quantum machine learning algorithms, I would like to just have a quick overview of what we have seen through some no what we say questions. So you can reply in the chat box if you know this answer. So a quick recap of what we have studied, just reflection. So which principle allows a qubit to be in multiple states simultaneously? You can reply in the chat box if you know the answer. It's just to understand where you stand in this concept of quantum, because we are discussing about quantum machine learning. But before we go, I would like to just have a quick overview. You can reply in the chat box. You can tell the option.
uh, the principle of qubits entanglement and superposition, sir.
Yeah, I understand, but we are asking only about the qubit. Which principle allows a qubit to be in multiple states? At a time, a bit is in two states, right? So what is that main
Yes,
principle?
sir.
Okay, some good
Entanglement, sir.
answers. Okay, let's see what is the answer. You can reply in the chat box. Yeah. Okay, few are telling entanglement, few are telling superposition. Okay, so good responses for this. I think the answer for this is superposition. Superposition is that principle which allows us to know, which makes that bit to be in both the states. When you measure it, you will come to know whether it is in 0 or 1. But otherwise, superposition is that one principle which allows the bit to be in multiple states at a time. Okay, good attempt. Yeah, next one. Which gate puts a qubit into superposition? We know, yes, bit can be in two states, either
Admart
0
gate,
or
sir.
1. So which is that gate?
Admart
I
gate.
request, yeah, I request you to reply in the chat box to avoid,
Admart gate,
yeah.
sir.
Okay, good number of answers.
H gate.
H gate, sir.
Yeah, H gate, right? Good attempt, thank you. Yeah, next one. The blast sphere is a representation of all possible classical bits, all possible qubits, measurement results only, or quantum circuits. What is your answer here?
All possible qubits.
All possible qubits. Very
Qubits.
good. Yes. I think everyone, all the participants are able to understand. This just to make sure you have learned a lot about quantum in the last few days. Because I'll be directly talking about machine learning part here. So I just want to know whether, yeah, this is all are very simple questions, right? I think you had a session on cryptography as well. So this final question, which cryptographic method is most threatened by quantum computers? Or which cryptography or encryption algorithm is most affected by?
RSA.
Let's see for other answers. Okay, good responses. Thank you. Yeah, I got an overview. You are very good at basics of quantum. Let's jump into today's learning, that is integration of quantum with machine learning, right? Yes, thank you all. I got my overview of where you stand in this concept of quantum, because some of you might feel still it is difficult, because I will be going little into the circuits, gates, all those concepts. So to make sure that you are understanding it better, I had just a small thing. Yes, obviously the answer is RSA, right? So the topic what I'll be talking today is little about quantum computing, then quantum ML foundations, the most important variational circuits. We'll be talking about variational circuits, and then a small demo of executing a quantum or a what we say a simple classical ML algorithm with quantum. So we'll see a small demo using Python Jupyter or in Google Colab. I will just give you a demonstration, and then we'll discuss about the challenges and research directions. So I think the most important learning for you from this session should be understanding about variational circuits. Again, that's what the core idea for how quantum machine learning works. And the other thing should be the research directions. So these two things should be very important takeaway for you from this session.
603
Yeah,
2426 291.
thank you. I got some code. Okay. So yeah, the first important question, right?
265.
Quantum computing, does it belongs to, because we are hearing about quantum, lot of people.
All the participants are requested to please keep your mics in mute. Thank you.
Sir is muted, I think, ma'am.
Sir,
Sir, you are muted, sir. Hello?
sir, are you audible?
Yes,
Vinay Raj,
can you
sir?
hear me? Can you hear me?
Yes, yes. Now
Okay.
it's here.
Yes, sir.
Is my slide visible? Slide visible?
Yes, sir.
Yes, sir.
Can you please share the screen, sir? Your video is visible, sir.
Okay. Thank
Yeah,
you.
it's visible, sir, now.
Yes, yes. So we are talking about quantum. During my engineering days, people used to talk about quantum mechanics, quantum physics. Then mathematics, people talk about quantum mathematics. We computer science, because I am from computer science background, I talk about quantum computing. And today people are talking about quantum engineering. So whom does this quantum belongs to, right? So physics is the one where it all began, because the concept of superposition and entanglement, or the concept of qubit, has come from physics, right? But the mathematics people have actually given the voice for it with the foundational mathematical concepts, because we talk about lot about mathematical foundations in quantum computing. And what about engineering? That's where it started building things, and as part of that is computer science, right? Once when the earlier we were not talking much about quantum computing, we were talking more about quantum mechanics, quantum physics. But after the what we say, the computing, it has been linked with computer science. We are talking a lot about quantum computing, taking advantage of the speed or other benefits of quantum, right? So quantum doesn't belongs to any single branch, it belongs to everyone. Actually, if you talk, no, it's a melting pot of human curiosity, where physics meets logic, math meets code, and imagination meets engineering, right? So this is one simple thing. Quantum computing doesn't belong to anyone. Earlier we said machine learning belongs to computer science, but today everybody is using machine learning. Same way is the quantum. Right, a generic simple diagram showing us how a quantum computer works, right? So you have a classical computer in between, you have a classical computer in between. Yes, right. So from the in front end, whatever we have, we connect with the quantum computer, and the classical computer sends the request to the quantum computer. From the classical, it goes to the quantum computer. So in simple terms, you understood what is quantum computing or what is quantum computer. It is taking all the data and converting into the quantum data, and doing all the no in the quantum registers, we are performing the operations, and we get back the results, right? Simple diagram. And just a overview of what we are seeing, classical data versus quantum data. So yes, you have answered very nicely all the questions. We in classical, we talk about binary 0 and 1, on and off system, but in quantum, no, we have only one state, that is we call that bit as qubit, which can hold which can simultaneously, it could be 0 or 1, right? So here in classical, logical gate are the building blocks, whereas here quantum gates are the building blocks, right? Why quantum gates here? Because we know we have to show this state. We have to represent this 0 and 1 in a single bit. For that, we have a specific kind of gates called quantum gates. You have already seen this. And logical gates here are made of transistors. Here they are represented by matrices. Okay. And here we talk about microprocessor, because it is the one on which we have all these transistors, resistors, and the bits which actually play the game. But here there is nothing such like microprocessor. Its game is all during the computation. When you are actually computing, the bit changes its state into different either 0 or 1, and it helps us in solving the problems. Another thing about qubit, here in we say bit 0 or 1, then we have probabilistic bit which could be between 0 and 1, and the qubit which can be both 0 and 1, right? Here we have two states. Here it could be between 0 and 1, sorry, in this it could be between 0 and 1 probabilistic bit, and whereas qubit, it could be 0 or 1 at any point of time, right? So this I just quickly skip this. And different kinds of gates, this is also very important to know, because if you know the gates, again I'll just tell you why is this important. When you're talking about data, or when you talk about machine learning, you talk about data. When you talk about data, you have to represent the data. So here in quantum, we represent the data in gates. Using gates, we try to represent the data. So your data set is not in the physical entity. It is not in form of a entity. It is no longer an entity. it becomes a gate. Your data is represented as gates in quantum, right? So that's one thing we should know, this basic gates. I hope you might have already studied. A quick revision. We have H gate, we have Pauli X gate, Y gate, Z gate, and controlled NOT gate, right? So in comparison, we also have about no this classical gates. We don't have any XYZ gates in a classical gate. We only talk about basic no universal gates, XOR, XNOR. We talk about them here in classical, whereas in quantum we talk about these different types of gates, right? H gate, XYZ, and a NOT gate. Okay. So quantum gate, we give the input, and here we represent as circuit. So these are the different representations, H, X, Y, Z, and this is a symbol denoting the NOT gate. Okay, and we also have a matrix representation for them. I think this you might have already studied. Sorry. Yeah, again, this is also a comparison between classical data. This is very important because we are talking a lot about machine learning. When we talk about ML, we also have to talk about data, right? So in even in classical machine learning, the data is represented in bits, 0 or 1s. Here we represent them as no gates, or we will represent them as what we say different possible states. So bits 0 or 1, here it is 0 and 1 qubits, right? So here if you see, the state is two possible exclusive states, here two possible simultaneous gate states, anytime 0 or 1, right? Representation vector of 2 dimension, here it is only 0 or 1. So always here we have a vector of 2 dimension uh, in qubits, right? Here we use logic gates, here we use quantum gates. All rest things are fine. This might have seen. Yeah, let's jump into quantum machine learning. This is a very, very important slide to understand. If you understand this, maybe you can understand the whole idea behind how classical machine learning works or how quantum machine learning works. Okay, so there are 4 different cases actually. What is this? See, I will talk about 2 important points. One, data is generated by a quantum device or a classical system, and the data is processed by a quantum or a classical computer. Okay, so these 2 things, you have data. Data could be classical data or a quantum, or and the processing device which I'm talking about, it could be by classical computer or a quantum computer. So these 2 things are important to us to understand the quantum machine learning, right? So 4 different approaches are there. You have to understand this concept better to understand QML in detail. See here again, when what is this CC? CC means data is generated by a classical system and it is executed in a classical computer, or in a classical approach. I am solving that problem. I am not using any machine learning there. Again, classical machine learning model, I am trying to solve it. So the data is from a classical system, and I'm trying to, that's what we have generally we have been doing. All of us in the course machine learning, what we do, we take some classical data, we execute that in some CPU or GPU, we compute them, and we try to get the output. That is our CC, right? What is this? Maybe CQ. Let's talk about CQ, the second one. Data is generated from a classical system. Normal data, this is normal image data I have, or some CSV file of data I have. Normal, if you have done some machine learning algorithms, if you have trained, if you have designed some model, you know what is classical data. Any data in general, what we talk in machine learning is classical data. So that classical data I am taking, but I am executing in a quantum computer. I'm executing in a quantum device. So this is the alternative. Data remains classical, but I execute in a classical environment or in a quantum environment. Okay, next point. Data is from a quantum source. Okay, data is generated from a quantum source and executed in a classical environment, or the fourth one, QQ. I hope you understand what is QQ. Data is generated from a quantum source and executed in a quantum machine, right? I repeat this because if you understand where does QML stands. Definitely it is not CC, right? we don't talk about machine learning in CC mode. Okay, so we don't talk about QML in CC because it has no quantum thing, but other three has the linkage with the quantum, right? So again, I quickly revise and make it clear for you. These 2 points, if you remember, data is generated from a normal classical system in any normal format, and it is executed in a normal system using a classical machine learning approach. That is type 1. Okay, this is type 1. Next, data is generated from a normal classical system, but that is executed. The data is processed in a quantum device. That is 2. In reverse, counterpart to that, data is generated from a quantum source. It's a quantum data, and it is executed in a classical machine. That is 3, which is very rarely we do this. And the fourth one is data from a quantum source and executed in a quantum device. That is 4. Okay.
Sir,
Now,
third one is possible, sir. The data was generated, data will be
from a quantum source,
generated
yeah,
on.
yes, it is possible, but if the data is very small, that's why I said no, which is very rarely we use this. Very,
Why?
very.
Because the quantum data is processed by the normal computer, classical computer.
Yes, yes.
But
If
data is
if the
quantum
data,
data.
yes, if the data, again, there is no difference. Again, next slide I'll talk about how to convert this quantum data to classical data, how to translate this to this. So this is what we are going to study next. So you will understand it much better, because if we, when you have a classical data with you, let's talk about the CQ, the green one, which is our primary focus today. We are talking more about CQ. I have a classical data with me. I am unable to solve that. I am unable to process or build a model on classical data with my classical machines. So I am approaching machine learning, quantum machine learning. So I'm going to a quantum device saying, this is my classical data, execute in a quantum machine and get me the output. Okay, that's what I made it in green color. That is what our focus is. But these are different classes which have been proposed. The possibility is there. This is still exists. It is possible. But for that, you have to translate your quantum data into your classical data, which is again not required to do. If you are having a quantum data, it is no longer required to convert into classical and then give it to classical machine. You can give it to quantum machine itself instead of translating it, which is of no use of translating QD, quantum data, to classical data. Okay, so this is just to understand different classes, and our focus is on CQ. Let us talk more about this. What are these 4, right? I think you got idea already what is this for. In case of classical data being processed classically in conventional approach, that's what we are doing. Without quantum, whatever a machine learning we are doing is CC, right? So it refers to ML based on methods borrowed from quantum research. It could be. Next is QC. It investigates how ML can help with quantum computing. In QC, we talk about how ML can help in quantum. I hope now you got here. I am talking about QC here. We know, little tricky to understand. We know ML is helping us in lot of things. It is helping us in processing lot of stuff. It is in classification or regression. You use in deep learning. You use in agentic AI. We have in AI in general. Machine learning is helping us in solving lot of our basic problems. Can the same machine learning help in solving the problems of quantum? That's what this second is about. The case QC investigates how ML can help with the quantum computing. So there might be some challenges in quantum computing also. And how are we leveraging on the concept of machine learning in quantum? That's what the second quadrant QC is talking about. Okay, see, many ML models could be useful to determine the internal state of a quantum computer. In quantum computing, I may take advantage of machine learning and solve some problem, which are the challenges in quantum machines. Okay, there I am not integrating machine learning. I am taking advantage of machine learning into my quantum system. That's what QC is about. So in that case only, you have quantum data with you. You apply some ML algorithm to this quantum data, and try to solve the problem. Okay, that's what we had QC. Next, CQ, right? In CQ approach is to design quantum algorithms for data mining. Again, data mining here, it's a simple word. I will say AI in general, right? So this is what our focus is. We are talking about QML here, right? So how do we design the quantum algorithms for solving for AI in general? And in QQ, we look at quantum data processed by quantum computers, right? So everything has advantage. Our focus is on CQ. What is CQ? I have classical data with me, which is normal machine learning data. It could be image, it could be video, or it could be text or CSV, anything, right? That data, I'm instead of doing in classical machines, I want to execute in quantum machines. I want to train the model, I want to build a model, I want to classify the data, I want to cluster the data, I want to apply k-means algorithm, SVM algorithm, all that technique in quantum machine, not in my local machine. But how do we do that? Let's try to understand that. This is one very important for us to understand. So if you understand the 4 quadrants, you will understand about this thing here. See, you are well known about this classical. I have classical data, I give to ML algorithm, I get the output. So the main point here focus is on CD and QD. Okay, CD and QD. So in classical, we give the classical data to ML. That's what numerical data or the form which we can see, we can understand. I'm giving images, I'm giving some CSV file, I'm giving some numerical data, some text data, which I can see and understand. In simple ways, you can say that way. So that is our classical data. I get the output in classical form, right? Whereas in quantum, you see, I have classical data with me. I do transformation of CD to QD. That's what, how we do, we convert the classical data in simple terms. Let's say numerical data. Let's say I have numerical data. This numerical data we convert into quantum data, that is we convert that into gates. We store that information in terms of gates. We represent them as gates. That's how QD looks like. Okay, so quantum encoding, here once I have the classical data, I do quantum encoding. I transform this classical data into quantum data, and then I give that quantum data to the quantum machine learning algorithm, which is not in normal form, which is in form of gates. That machine learning model will give me output as quantum again. Again, I do the measurement. So I think you know this. This should be one of the MCQ questions. If you measure, what will happen? When you have a qubit, if you measure it, it converts into normal bits, binary bits. So when I do measurement, that QD will be transformed into normal data, which we understand, and we get the output. Right? Simple as that. This is quantum. That's what I think. If you understand those 4 quadrants and this thing, that is the whole picture. So we should know how to do this encoding and how to do this measurement. We need not know, computer is doing it. You have a lot of, again, quantum computing, computer itself is that, computing itself has that advantage. With Python programming, you just give the command, you just tell the algorithm which you want to execute, it will automatically translate that data which is in numerical form or in CD form, classical data format, into quantum data. It will automatically take that, convert it, solve it, again give back you the classical data. Okay, so in the demonstration, we will see how this process happens. How is that conversion happening? Right. So we will understand more little about quantum machine learning. Then we'll go back and understand about the. We'll go and execute the case small, demo. We will see how is this process happening. Right, from this data to this, then this step given to it, how it is transforming back as the output. Okay. So we were focusing more about the CQ setting. I have the classical data, and because you need not convert the data into quantum data and give it to quantum machine. We don't have any quantum data. It's a big challenge. That's what we will see. What are the challenges in quantum machine learning now? Right? The whole game is going towards these 4 quadrants. Right? This anyhow is classical thing. CQ is what we are discussing about, but QC and QQ, where there is a lot of scope future work which can be done. I'll be discussing them in the future work. So we are talking about CQ setting. What is the CQ? I have the classical data with me. I have the classical data. I give it to quantum machine for execution, right? So there are two, again in this, there are two points. One is translation approach. Okay, so based on the translation of a classical model in a quantum setting. So what is this? You heard about regression. Lot of regressions are there. You heard about SVM, support vector machine. You heard about k-means clustering algorithm. All these are basic machine learning algorithms, right? How do you implement them in quantum setting? Means you know how k-means works. You know how regression algorithm in machine learning works. You have to translate this regression algorithm in basic machine learning into a quantum setting. That's what, no, only then I can do it. If I just go back here, I have classical data, I am converting into quantum data. This I can do, this I am talking about, right? But classical data is given to classical ML algorithm. To feed this quantum data, I should have quantum ML algorithm. From where should I get this? This translation we are talking about, this we can do this translation, we can do that. But how are you translating this from classical machine learning to quantum, right? So for that, that's what this is about. So translation approach is what you do, general logic of the model is maintained. That is, regression means it will do prediction. Same regression logic is maintained, right? A part of is delegated to quantum computer. There is no change in when I talk about let's say SVM and quantum SVM, right? The only change, what we are seeing in SVM, a normal machine learning algorithm and a quantum machine learning algorithm, is that quantum, a part of this SVM, there are a lot of steps in SVM algorithm. Let's say a part of that algorithm is sent to quantum computer to process it and get back the output. That's what is, we are calling it as QSM. Otherwise, it's nothing. It is just out of maybe 10 steps in SVM, 6th and 8th step, let's say, I am giving into quantum computer, quantum machine. I am giving it to solve it and give the output. That's it. For that, we are saying it is quantum machine learning, right? So this is just an example to tell you what is the point I am trying to explain. Translation approach, right? General logic is as it is. SVM logic is same. K-means logic is same. Regression logic is same. But a part of that computation is sent to a quantum computer to execute and give back the output to us. Why are we giving it to that? To speed up. Only to speed up the algorithm, right? That is basic again. Again, in CQ setting, there are two types. One is translation approach, other is exploratory approach. I hope this also you understand. So we are narrowing down a lot, right? From the 4 quadrants, we are coming again to we have chosen CQ. In CQ again, I have two things, right? So translation part, I run my basic machine learning algorithm. Some part of that computation, I am giving it to a quantum machine to execute that particular computation step and give back the response to me. Because of that, what happens? Speed improves. No change in that. I am giving classical data only. I am having classical data with me, that I am translating it to quantum data and giving that to a quantum machine. Only one step or two steps, which are very tough to do in classical machines. Why I am doing that? Because to just improve the speed of the algorithm. Basically, all ML algorithms are doing better. They are doing good in classical machines itself. There is no need. That's what my conclusion is. Okay, we'll talk more about at the end. What is this exploratory approach? Here, we are taking advantage of any system obeying the laws of quantum mechanics. This is the core part. Here, what we are doing, right? We are trying to build a system which is a quantum, which is following the principles of quantum. I am building a system which is following the principles of quantum, right? To train a model that is about to learn. So the training of the model, I am doing it in a quantum machine. Okay, again, I'll just go back and clear this part again. I'll go back to the 4 quadrants and the 2 types of data and this part, so that you understand where does this QML actually stands, right? In CQ setting, we have two types. One is translation approach, where you have classical data with you. You can run that in a classical machine, classical computer or a classical machine, but it is taking time. For that, what I do, some part of that algorithm, some steps of that algorithm, I send it to a quantum machine to execute that faster and give back the response in my algorithm. Simple approach, right? Why? Simple to speed up, nothing else. The second one, I have a whole system. I have a whole system with me, right? The training of the ML model completely it is done in a quantum machine. It is done here. Okay, so it does not have no a classical counterpart. Means there is no other system on the other side. Here for first step we have the other side. No, I'll just go back here. In translation thing, you have classical data, you have classical machines, and you run classical machine learning algorithms. Simple. But to take advantage, what I'm doing, converting something into quantum data and giving into quantum machine and executing quantum machine learning algorithm and getting the output. Both are giving us the output. In second thing, here I told you only partial is given, only partial no thing is done. Whole algorithm is running in classical only. Some part of it, some part of that classical model, I am taking advantage of this, right? Whereas in second, I have only quantum data, I have quantum machine, and I run quantum ML algorithm. There is nothing about classical. That's what the explorative research is about, right? So this is about the in CQ setting. We have two ways, okay, but ultimately quantum is mainly for speed and security, two aspects. Okay, we will talk more about this in the conclusion. So yeah, but why do I have to go for QML? Is it really required? Is the question. Why are we talking about quantum machine learning? Is it really required or not? If you have done some execution or in the demo which I'm going to show, you will understand, you will not feel any much difference for simple algorithms. Yet there are challenges. Yes, there are so many open research problems which we can solve. Yes, there is a lot of scope in QML. We can work on that. It is required, but not for all the cases, right? So that's what we will prove with the demo which I'm going to show. You will see that there is not much difference between a classical ML model or a quantum. Whether I'm doing that in quantum setup or I'm doing it in a classical setup, output remains same, right? But that's what we will see. Why, if at all you are moving towards quantum ML, what is the advantage you have? That we will try to understand, right? So there are four different dimensions in which we have to look when you are thinking about comparing classical thing versus the quantum ML, right? What are those four dimensions? So one is computational complexity, second is sample complexity, robustness, and model. I will talk detail about this. What is this computational complexity? I think you understood. Runtime, I want to speed up, right? Computational means runtime complexity. So basic things takes more time. In classical, I go to quantum. It speed up. It just speeds up the process. So we get quick output. That is one thing. But really, are our current? I think only today we have supercomputers. We have GPUs of high-end GPUs. So they are also doing in better time. We need not go for. There is not much need to move us to quantum. Okay, we will see there are some problems which can be done using quantum. So we'll talk about that. But the advantage, if you're looking for, if your goal is to reduce the speed, choose QML. And you have to prove it that no, classical is taking more time. Second one, sample complexity. This is the most important one, right? So number of samples needed to generalize from data. Data is the heart of machine learning. When there is large data, your model is nicely trained, it can do better predictions. So the more the data, the better is the model. Old saying, not now, but if you are teaching machine learning, you say this: the more the data, the better is the model, right? So in the same way, if you have the sample complexity is talking about number of instances required to learn, okay, to understand, to identify patterns in the data, we should have more data. So if the data set is very small and you are feeding it to a quantum, it doesn't make sense. So if the sample, if the data sample means I'm talking about data. I think you in statistics we talk about population and sample. So that is the sample, right? So sample data, if the data is good amount, only then we can look after quantum. Then noise. Yeah, this is very common thing. We know we have a lot of noisy data in machine learning. So when the noise is there in the machine learning data, we get a poor model. So when you're getting a poor model, it's a failure. You cannot do, it cannot do better predictions, right? So what you can do here, right? So this, what we do to avoid noise, what we do, we actually flip the data. I think somebody working with image processing might know how they do the transformations to the rotations, to the image data, right? You do it horizontal, vertical, lot of transformation rotations you do there to generate more accurate or good data, right? So here, even if there is noisy data, QML can still learn effectively. Okay, that's what the simple point is about. And the final one is model complexity, expressive capacity of ML models. Okay, so complex model offer higher flexibility and capacity, managing to learn complex laws from the data, right? So ultimately, if you are moving towards QML, your goal should be, if you are looking for speed, yes, you can go. If your data is very huge, you can go for QML, right? If there is noisy data, you can go for QML. That's not a problem, right? And the model complexity is very high. Let's say your deep learning model is of big size. It's also in GBs. When you're saving the model, it's also not in MB, it's in GB. Let's say very complex model. Lot of computations are there. Then also you can think about QML, right? So these are 4 different aspects when you have to look for when you are actually thinking of moving towards QML. So this is just a simple thing, how you do in basic machine learning model. You do a lot of pre-processing steps. You apply any of these algorithms and you use these metrics, right? This is simple ML thing. You either use basic ML, you do lot of data pre-processing, you get data from different sources, then you do pre-processing, then you train your model, and then you evaluate the models. This is basic ML. Whereas in quantum, what we do, right? You actually do very important step is encoding, right? I think this encoding to qubits is an important step. You get data from different sources like we get in machine learning, but in during deep pre-processing, data pre-processing, I'm actually doing encoding of the bits. Okay, then I am feeding it to the quantum ML models, and then I am trying to evaluate that. So when I am evaluating along with this basic metrics in ML, I also talk in terms of qubits and repetitions, right?
Sir,
So yeah, please.
sir, this is Dr. V. J. Prakash, Associate Professor from PSMR College of Engineering and Technology, sir. Sir, how can you convert this classical data into
Quantum data.
Quantum data, sir?
Yes,
Give
yes.
me
We
one
will see.
example.
Yeah, we will see the demo. I will show you the demonstration when I run that in Python programming. How it is happening, it's again a different subject, but I will show you how it is actually doing it. You can see the visual. It will generate the gates. I think that should be done. You might have, did you study about gates in quantum? I think
Yes, sir.
I believe somebody might have told you about this simple example, how these 4 binary states are converted into quantum gates.
Yes, sir.
Yeah, this thing we will see. I will show you how it is happening. It can be discussed, but I will show you when I give some real ML data, how it is being converted to quantum data as gates. I'll show this demonstration.
Okay, sir. Thank you, sir.
Yeah.
Sir,
But again, you need not know that how it is happening, because programming is, computing is taking care of that. You are just you are having classical data with you. You are what we say, you're importing some Python libraries. Those libraries are actually doing this transformation. You explicitly you are not involved there. because you have just you have to write some command which will translate this to this. Okay, and this will
Okay,
be
sir.
fed to the ML algorithm, QML algorithm, and it will give the output in CD. This is automated now.
CD.
Yeah, so from computer science perspective, it is of less thing for me because I want to take advantage of that QML. I don't want to know how it is working as a black box might be. But if you think about EC perspective, you should know how are those gates constructed. I think that's a basic thing what we teach in quantum computing. How are those gates constructed? Not this CD to D, but actually how is the data binary digits 0010 or 000, all those are constructed as gates. We can see that, no problem. So yeah, so
Thank
we
you,
were
sir.
talking about this classical and quantum. So here the important step is this encoding. Like you have asked, we are of least bothered for now in this session because our goal is to understand QML. How it is working could be another session maybe. So we also take no.
Sir,
Yes, please.
sir, what is the use of quantum computing for the images?
uh, Again, when we talk about quantum image processing, we know our current deep learning models, which are based on again image processing models or quantum deep learning model, basic deep learning models, accuracy is not up to the mark, and it is taking a lot of time for training. So when you're working on image processing, you can use this quantum for speed. That's it.
Okay. So
Only,
it won't take
only we
much
will
time
increase.
for the encoding operations, sir.
No, it is also it is quick again. It is again, that's what no our when I talk about conclusion or the future research problems, there are research quantum actually, I'll tell my conclusion here. Quantum actually is for very large data, and if you're looking for speed and security, wherever there is some security aspects, right? If you're talking only there, it
Okay.
is useful. Otherwise, your basic deep learning models are suitable for image processing. Only since quantum is trending, if at all tomorrow there are hundreds of GB of image data with me, then only I will look after quantum computing.
Okay. Okay, sir. Thank you.
Yeah.
Sir, one more doubt, sir.
Yes.
Sir, so here, while we are working on machine learning, so you have to maintain more data as per your
Yes.
presentation.
Yes.
You are maintaining more data, so the processing speed may be slow down
In classical.
in classical.
Yes.
So, and you told that the data should be in sampled form.
It should be in quantum form if you are feeding it to the quantum machine.
Commercially. So as per our sampling theorem, you have to maintain half of the samples, sir, out of total. And suppose in image you have 1000 pixels. Out of 1500 samples are sufficient to recover the original image.
Yes.
But here you told that you have to maintain more number of samples.
Again, that's why I said no. That's an old saying. I said the more the data, the better is the model. Means we in general, I'm talking about machine learning. When you have a huge data set with you, that model is trained better and it does better predictions.
Okay, okay,
So
okay,
data
sir.
should be more. But coming to image, what point you are telling, it's one subset of that. It is one point where we say this much data is enough for identifying the image, which is actually equal to. That's what quantum cannot be applied for image processing. Quantum cannot be used for big data.
Hmm.
It is used only for speeding. If there is a
So,
complex, if there is a complex step involved,
yeah,
which
yeah.
is more time consuming, that we can give it to quantum.
Hmm.
But we all are doing business to take advantage of quantum to produce better research, to write more research papers. We are saying quantum image processing, quantum big data. We are talking about quantum ML. All things are, we are just including quantum into picture. Or otherwise, quantum is just for speeding. If there is something which has security problems, we can go for quantum. If there is something which requires more time to execute, we can go for quantum. That's it.
Okay, okay, okay. Thank you, sir.
Yes. So I think you got idea about how classical and quantum ML are working. This is different types of algorithms in quantum. this is again a much more thing to understand. We will see about that to an example. Yeah. So one final concept to discuss, variational circuits, right? Then we can move for the demo. Okay, what is this? So when I am talking about, right, classical data, sorry, I am talking about classical data, then converting to quantum data, then giving it to quantum machine learning. Again, I am getting classical data. This is what we have seen today, right? So what is this variational circuit? What is this? What game it is playing in this whole cycle from CD to getting back CD? Let's understand what is this variational circuit. This is the backbone for QML. Okay, what is this? Simple thing. See, you assume variational circuits, quantum circuits as quantum brain. Each quantum gate is a neuron. Each quantum gate is a neuron, adjusting their angles like a learning from the data. Right? Over time, the circuit becomes better at solving a problem, whether it is classification, optimization, or pattern recognition. Now let me tell you what is this. I'm talking about this. Right? So you know about neural networks. In deep learning, we say neural networks, the layers, right? Input layer, output layer, hidden layers. The more the layers, but more is the complexity of the model, the better is the output. In deep learning, we say there, right? You should have more number of deep learning layers. Again, we should not have, depending on the problem, we keep adjusting our number of layers in the deep learning, right? In the same way, to implement QML, right? We need to take help of this variational circuits. Okay, it is like a quantum neural network. It consists of quantum gates whose parameters can be tuned. Right? These circuits learn patterns in data by minimizing a cost function using classical optimization algorithms. So when you are saying training a model in machine learning, when you are saying you are training a model, you are actually learning the patterns in the data. Based on that pattern, when you give a new data, it is predicting and telling the cost could be this much, the gold price next year could be this much. So it is understanding the pattern. It is seeing what is the percentage of increase in the gold price in historical data or past few years, right? In the same way, this variational circuit, okay, or the quantum circuit plus the classical optimizer is a hybrid learning system that evolves intelligently. So it is like the AI model. It is learning with experience and evolving, giving better results. Right? In quantum context, we talk about variational circuits. Okay, it learns. It learns by solving by repeating the process. It learns the patterns in the data and gives better outputs. Okay, we will see this one simple technical part of it and then come back to this. Okay, since the use of real quantum computers is still today either very limited, we are not using this, and also impossible to use, right? The use of some hybrid algorithms able to run either on classical or limited quantum devices is growing. What we are doing, we are not having pure quantum machines with us. It is just all theoretically we are proposing it, but we are not having it, right? But how are we achieving that quantumness? In our quiz kit, IBM quiz kit, they are telling maybe they have there, but somebody is doing some experiments in quantum computing, right? How is that actually happening? Yeah, thank you.
And actually are creating Kawasaki songs.
Hello, somebody is disturbing you. Madam, please mute yourself.
Yes. So this variational circuits, we are actually not having any pure quantum machine. We are just trying to we are recreating the quantum setup and doing that. So how is that actually happening, right? See this thing, this one part, if you understand, you get what is this. See, the variation algorithms, their foundation is to evaluate the value of a given objective function c of theta, where theta are a set of classical parameters. Okay, so to optimize them, right? We don't have classical computer, we are just recreating them with the help of variational circuits. Okay, why are these circuits required? See, they bridge the gap between classical and quantum worlds. Okay, and adaptability. These VQs are more flexible to model complex data relationships. Neural network, again, there is some problem which I can solve it using machine learning, but still I can solve it using deep learning, a neural network model. Why? Because it is no, it is nicely representing the data in different levels, and it is understanding each level and doing it better. So even in quantum, to understand the data better, we need these variational circuits. Okay, these VQCs can tolerate some noise, right? And these VQC are the foundation for QML algorithms like quantum SVM, quantum
Sir, you are in a muted, sir. Sir, your mic is on mute.
Vinay sir, sir, sir.
Sir, Vinay sir, your mic
Yeah,
is
yeah.
muted.
Somebody is muting me. I think I don't know. Automatically, it is going. Sorry.
That's okay, sir. That's okay. Now it's
Yes.
audible. It's carrying.
Okay. So the variational circuit, the counterpart in basic ML is neural networks. Okay. So if you understand what is neural network, what it does in ML or in deep learning, same VQC does here. So we need, because we don't talk about much about ML things, we talk more about deep learning, which is actually doing the basic AI implementation. Same way we need this VQC, no, in the quantum ML algorithms. Okay. So a lot of variation algorithms we have in we talk about CNN, we talk about no ANN, we talk about lot of neural networks in deep learning. Here also we have some kind of variation algorithms. So first one is eigensolvers. Then we have approximate optimization algorithms. Then we have cloud-based services as well, and deep neural networks. Again, deep neural networks. They are here using variational circuits. Okay, so this VQC is one of the very important concept to understand more in detail about QML algorithms, right? So I go back to this point again. I come back here. Let's try to see one small demonstration, very simple example in a simple way. How is this step happening? How is it encoding the no classical data into quantum data, and again getting back the output in the classical form, right? Let me share my screen. I'm just sharing. Give a second. Yeah, I hope it is visible. This is again in Google Colab, a very simple example. I have it here. So yeah, so I just want to demonstrate the simple ML flow. I'll just skip it. You know it better. But about the QML flow, converting that data in what we say classical data to quantum data, right? So basically, in Colab, you have to install some packages first. I think IBM Qiskit is one openly available for all of us to play with quantum algorithms. So we have to install certain algorithms. So this thing, so one is Qiskit default package, which we have to have it with us, right? Qiskit, and then Qiskit AER. Then for Qiskit machine learning, we have this QML, right? This package also we have to install. And scikit-learn is basic thing. This is for running, executing basic ML algorithms. So certain packages we need to import, okay, install them because we don't have them in this setup. So I'm just executing this. I think pip install command I'm using to install these algorithms. Okay. Yeah, it is executed. So I have installed this what we say quantum related packages in my environment. in my Python environment, I install those things. I think you are aware of scikit-learn. Without scikit-learn, we cannot do any ML thing. So that is because I'm just comparing ML and QML. Okay. After this, I am taking a small data set. Simple problem, binary classification. Okay. So I have size and weight of coins. Okay. My question here is, my simple problem is to classify the coin, whether it's a fake coin or real coin. This simple problem I have taken to demonstrate that. Okay, so I have two features only, a simple data set, size of the coin and the weight of the coin. Okay, so there are two classes, 0 and 1. 0 means real, 1 means fake coin. This is just to demonstrate what is the advantage of quantum. Not for this, this is just to make you comfortable with executing quantum ML algorithms, even in our basic setup of what we say ML setup. So I am representing the data. I have the data, very small data I have. So each one is a record. This is size of the coin. This is the weight of the coin. So I have some simple data with me. This is a basic ML thing. Importing NumPy, and then I'm using sklearn. I'm doing this model selection. I just execute this. Okay. Yeah. So now I will split this data into training and testing data. That's what basically we do in ML part, right? So I come here, I do this also for you. Yeah, I have splitted the data into testing and training data. Okay. Now, this is the classical ML part. I am just implementing logistic regression. Thank you. So this is a simple logistic regression model I'm using here. This is basic ML thing. So you can see the accuracy I'm getting 1 because it's a very small data. No, you are getting accuracy as 1. This is done. Okay. Now we come to the actual part. Right. So quantum thing. How do I execute the same thing in quantum? Okay. So we here if you see the data is in classical data, and I'm not seeing any output, but accuracy I'm getting here. But actually, if you want to see the output, what it is predicting, you want to give the new input, you can see the classical data outputs, right? Now come to the quantum ML implementation. Yeah, so I have already imported some packages. If you see, Qiskit is the framework, the basic framework on which I have so many other packages. Okay, then I am having QML, Qiskit machine learning, for executing the quantum ML algorithms. Okay, so I come back here. Yes. So how is this doing? Sorry, how is this actually transforming the data, right? So you have classical data. We translate it into gates. We represent the data in gates, right? So for that, I am using this ZZ feature map. This is one library which we'll be using here. And then I'm using fidelity quantum kernel, which is from the quantum ML algorithms. And I'm in basic SVM, I'm importing from the ML part. Okay, now you see here, right? Yeah, before I go here, see, when the data is in classical form, you may not be able to classify it. Sometimes the data is in complex structure. You may not be able to classify it. So what you do, you try to convert them into a higher dimension space. You take that data into a higher dimension space. I think you are getting my point. When the data, let's say I have, maybe I'll go back to my screen if I can share it, or otherwise orally I can tell you instead of these sharing it. See, when you have the data points on a plane, if it is nicely separated, you can draw a straight line between, classify the data. I have all the stars this side, all the plus this side, I can draw a straight line. It is easy to do. Sometimes the all pluses and stars are all clubbed together. From your, when you are seeing that, you are unable to draw a straight line there. So what you have to do, you have to project that data into a higher dimension space. So when you project that data into higher dimension space, maybe you can see you can, if you rotate the data in some higher dimension, you may find a proper view where you can draw a line and separate the points. So the data which is complex, or it is very tough to do classification, you may have to project that data into a higher dimension space. Okay, so there we actually have, we call that as a feature space, right? So what I do here, that basic quantum data, classical data, I take it to a higher dimension space. That I am doing it using this ZZ feature map. See, feature dimension equal to 2. I am projecting that data in classical form into a higher dimension classical form only, but I am taking it into a higher dimension space. Then I draw the circuit here. If you see, yes, so this is the circuit for that data. Okay, how is that being translated? So this is what we are feeding to the quantum ML algorithm. This is the quantum gate. See, we are having H gate here. I'm using this no computations here, and then all this gate structure. I think you might have studied how is this basics. If you know basics of gate, this is a interesting concept to learn how to draw, how to generate the quantum gates, quantum circuits. Any data in general in classical form has to be definitely transformed into a quantum circuit. Into using gates, it has to be represented. Only then I can feed it to a quantum machine, right? So this I'm just trying to draw this no ZZ feature map circuit. So here the data in classical form is now converted into this form, right? Q0, Q1 states. I have this. This is automatically generated from this data. Okay. Now I try to do the space. See here, I'll just execute this. So fidelity quantum kernel, this is actually transforming. If you see here, I have the classical data 1, 2, 3, 4. Using this no ZZ feature map, I got this in quantum. This is the representation here, right? Function phi of 1, 2, and then phi of 3, 4. This could be any state. It could be in any state. This is just an example to show you how is it translating. We are least bothered. You need not worry about the circuit. You need not worry about this. If you want to, if you are thinking in quantum computing perspective, only in computing perspective, these things are of less importance for us. If you are actually running, if you want to take advantage of quantum, of less importance, right? So this is just to show you how it is actually doing. This data here in classical form, the ZZ feature map is translating it into quantum form. See here, I'm having this representation in quantum form, right? So then I use my SVC algorithm using this quantum kernel and evaluate it. Okay, and I go and check the accuracy of this, I get the accuracy. So there is no difference. If I don't talk about this, if I don't talk about this conversion, there is no difference in the basic part or the quantum part. Okay, just for you to understand how is it actually doing internally, it is designing a circuit like this. The data is being converted into a circuit, represented as a circuit. Okay, using gates. Then it is fed to the quantum algorithm, right? How is the data transformed? See here, the same simple 1 to the numerical data here as a vector here. I have this in this format, right? See 3, 4 here using the ZZ feature map. I am having this in a quantum format, right? So that's what this is doing internally, or otherwise I have to just import my libraries, translate the data into from classical to quantum data and give it to your algorithm. Here SVC is my support vector machine in quantum quantum counterpart for SVM, right? This I am giving the quantum kernel dot evaluate, and I am then using my training data XY fit the model. It is actually doing the model, and then I am checking the accuracy of that. I can see I am getting the accuracy. It's a very simple data. Okay, so if you are looking at a quantum perspective, research problem number
Sir.
1, we can research problem number 1. Yeah, please.
Sir, here X train and Y train, what you have taken is it quantum data for the quantum model, sir?
Yes.
Is it a quantum data or a classical data, sir?
X train, Y train is my this data.
Means
classical data. Yes.
So for a quantum model, you are giving classical data and
yes.
checking the accuracy.
Yes.
Yes, sir. Right.
Yes. Okay. So point number 1, we have lot of challenges in machine learning and deep learning. You can choose some quantum system like this, train or build a model in quantum setup. Second thing, in quantum setup, when you are actually having this kind of the circuits, how you can do it better, how you can improve that. That's what we are going to see. But this is just a simple demonstration. If you have not done before, I think a lot of now I see a lot of people writing papers using QML. Even we are doing that. Simple. Uh, uh, there are 100 lakhs of papers in basic machine learning. You simply take them, run them in quantum setup, and show the improvement if there is an improvement, or you can just compare. That is one good trend going on now on quantum by just using the quantum ML, no, executing the same paper, same model, same data set in quantum setup, right? That is one thing which, if you easily want to gain some confidence on quantum, that could be one research direction you can think about. Okay, so in this demonstration, what I have done here, I have just imported few quantum libraries, and then I have used ZZ feature map. Okay, so what it will do, it will represent the circuit. It
Excuse
will,
me, sir.
yes, please.
Sir, for converting classical data into quantum, how to know which encoding techniques and which gates we can use it, sir?
For that, we have different
There are so many gates and so many
yes,
encoding techniques there, sir.
that's what.
How to
Again, yes, for that part, every algorithm in machine learning is using a certain types of gate. You should know, again, you can do it with any gates. Okay, I'll clear in simple way. Suppose I want you to build a NOT gate, let's say, in basic digital logic, if you know about NOT gate, simple NOT gate can be implemented directly, or I can use some XNOR on XNOR, or XOR on XOR I can do, double things I can do. Right. So we teach students in digital logic how, please represent this as a design. Somebody uses XNOR gate, XNOR gate, or NAND gate, AND gate, and they design it. Somebody may use simple gates, somebody may use universal gate to get the output. In the same way, here also we can have different gates. You can use any gate depending. If you know what is the gate actually doing, you can design it. And the circuit design is also taken care by the programming part. You give the input, it will design it for you. It will take care of that designing part. Okay, so for your question, which gate to use exactly, there are multiple answers for that. If you know what H gate is actually doing, H gate can do that, or Pauli X gate, Y gate can do that, you can use that. So it's all about what you actually want to do. Okay, so this is
okay, sir. Thank you.
yeah, right. So we have seen, again, I am getting the quantum accuracy with the basic thing, right? So classical data I'm executing there. Internally, it is actually converting this statement, right? My fidelity quantum kernel is actually converting the data. You can see here how the classical data space has been transformed to quantum feature space, how it is converting into a quantum format, and that is being given to the algorithm, right? So this is about a simple demonstration. You can do a lot of research. I think if you have not written any paper on quantum machine learning, or you want to take advantage of quantum, best thing could be take one classical paper which has solved a basic problem using machine learning. Take that, take the data, solve the same problem using quantum machine learning, and compare the results and see which one is doing better. You will see some differences, little differences in terms of inference time, the time taken to execute. That alone
Sir, you are
in basic sorry in basic what we say research, even 97.2 to 97.5 is a improvement. In the same way, you may see what are the improvement in terms of accuracy, precision, all those parameters, but you will see in terms of inference time. Okay, so that is one research idea you can implement now if you want to explore
Out of,
quantum thing. Okay,
excuse me, sir.
yes.
How can we evaluate this inference time in a classical machine learning, sir?
The computation time, I think it gives us the computation time, we can get it. You
Okay,
have some metrics
so
to
the
get that. Yeah,
computation, right?
yes.
So computational time for classical machine learning
It's
compared
not,
with the
it is not
inference
actually
time.
computation time. It's actually inference time, the time taken to, get the, again, yeah, in simple terms, it's computation time only. Okay, I'll not make it complex.
Okay,
Excuse me, sir.
so that is being
Yes.
Sir, you said that you can do any machine learning program with quantum.
Yes.
Is that machine learning program should be written in Python, sir?
Yeah, everything in Python.
Okay, sir. Only Python programs can be
Yes,
converted.
because we
Okay.
are going with Python is because we have this Qiskit library in Python
Okay, sir.
programming.
Okay, sir.
So we are going for this.
Okay, sir. Thank you, sir.
Yeah. Right. I'll just go back to my.
Excuse me, sir.
Yes, please.
For converting quantum data to classical data, you mentioned measurements, sir. Can you explain about that? How we can
Measurement is
measure the quantam data?
no. Measuring means, see, if you are trying to know the state of a qubit, it is actually measurement. Unless until you touch it, it is in qubit states. If you measure it, if you touch it, if you want to, in simple, if you print it, you will see some data, 0 or 1. When you touch it, it becomes its measurement. Yeah. So yeah, going back to some research things. Yeah. So this is what I was talking about the training of ML models. If you want speed, you can go for QML. Simple. That's what the summary of this slide, right? Then VQ, right? Variational quantum algorithms. This again, we talk about neural network, deep neural network, CNN, ANN. We talk about lot of models in deep learning. Same way, you can also have you can design lot of complex quantum circuits, right? So that the challenges in basic things can be recovered. For now, people are talking about in chemistry and in drug discovery, right? It is creating much more better results compared to the classical things. For that only we are having now the current research, but we are just exploring about ML part there. Okay, optimization again. Yes.
Do we have only these quantum machine learning algorithms which you have specified, sir?
No. There are many. That's what I'm saying. See,
Okay.
you have let's say you have one CNN deep learning model. That CNN can be recreated in quantum setup, taking help of these variational circuits. You can take help of variational circuits, design a new circuit, design a new QML deep learning model. That can be done. This is possible, but for that you should have good quantum environment. We have only Qiskit library or one or I think 2-3 are there freely provided for us to play with the quantum part. For now, it is said that you can do it for any algorithm, but in practical, very few has been done.
Okay, sir. The base is the variational circuits.
Yes.
Okay.
Yeah. So you can also talk about optimization. Again, these are all from some research papers, what I have found. But otherwise, if you really look into quantum part, the more research if you read some papers in Google Scholar, you will find more of taking advantage of the speed of that or talking about security aspects of quantum. But in terms of machine learning, if you talk, it's all in a learning early phase only. Lot of people are just implementing, taking advantage of quantum ML setup and writing some papers. That's what I have seen with my experience. Okay, so in summary, before we go to the summary, this is just QML is just an emerging field, right? It has lot of potential, but it is only in the experimental phase. Why? Because of hardware limitations. We don't have exact quantum setup. We are just using some dummy platforms, right? So there are two aspects. Quantum computing has some challenges which can be solved using AI, or I can solve some classical problems using quantum AI. Okay, so two things, but the first one is never explored. There is no work done in that area. Nobody has solved any quantum problem because we are not looking into that now. We are only looking how I can solve some basic ML problem using quantum. But some problems in quantum can be solved using AI. That's what people are telling. I read it from papers, is what I understood. What I have done research in quantum computing, we have just taken advantage of quantum. We are working in security aspects. We are trying to see which quantum algorithm is better in providing security, because RSA is breakable, right? RSA can be easily breakable. So we are seeing in software applications, when the systems communicate to each other, we are using RSA algorithm today in general. But how do I bring this no quantum algorithms into picture and make sure that the communication between services is better? That is one area we are exploring. Or the other one, just to create, as the market is moving towards quantum, we are also simply comparing. We are taking some classical ML paper, applying quantum ML, and seeing what is the improvement in the papers, in the results. That's what we are doing, right? I personally am doing. That's what here also I have mentioned here. We have lot of scope. If you are looking in research perspective, maybe you can work on security aspects and speed aspects. Only those two things are now important for quantum. I am talking as a computer science person, so I think only in computing aspect. So I am talking about security and the speed aspects of that, right? So again, one more research direction which I did not mention is hybrid part. Let me write it here. See, your hybrid setup means classical data I give in classical machine, I apply basic algorithms and I get classical output. This I know. Second one, quantum data, I give it to quantum machine learning and I get the back result in quantum. This anyhow I am translating it back to this classical data. The third one is the hybrid one. What is this hybrid one? Where you have classical data, you have classical machine, you give partial data, maybe some 80% of data for computing here and get the output, whereas the remaining 20% you give it to quantum machine and take advantage of the quantumness. Okay, taking advantage of the quantum to do this output. So people are now looking for, because I don't have such big problems. You are saying no, Google has done this, China has done this problem, 2.5 billion years it takes to solve, but they are doing in 1 second. We don't have, as normal people, we don't have such real big problems which really requires quantum. So what we can do, your classical papers, your classical works only, your classical problems only, you take advantage of quantum, some part of it. So lot of research is going on in hybrid context, because people will question why you want to go for quantum. Is your problem so big? No. Is it very tough to solve? No. Maybe you may have problems, but if you have, okay. If you don't have, then you should think about quantum, this hybrid approach, where you just rotate, no, divert some data to the quantum for speed or security aspects and get the job done. So this is one you can look after. So yes.
Excuse me, sir.
Yes, please.
How do we justify like which part of the data should be given for quantum machine learning?
It's not the data, it is the step which you are actually giving it to the what we say, quantum. It's not the data. Data remains same.
After splitting, then we will give part of the training data for classical machine and part for the
Yeah, this is
quantum
one
machine, sir?
research direction what people are looking for, because they want some steps to be done. Actually, it's not the data, it is the steps. Maybe I understood. I told you give 80% data and 20% data. No, it is 80% of steps in that algorithm in classical context and 20% steps using quantum machines.
Okay,
So
okay.
if I have 10 steps algorithm, 8th step is a very complex thing that I can get it done in quantum. So that's it. We
Is
have
it possible?
Yeah, please.
Is it possible that few of the pre-processing steps of the machine learning, which are complex in nature, can be done in quantum machine learning? Is that the way?
Pre-processing, to be frank, it's a very challenging thing in quantum, because for
Yes,
pre-processing,
sir.
your data has to be in quantum circuit, which is very tough to do. Actually, it is very, very tough to do pre-processing part.
So which steps can be done in quantum machine learning, sir? Like, if not pre-processing, then afterwards we will try to build a model, no, sir?
Yeah,
So
in model training,
those
model training, let's say I'm using some deep learning model. In that deep learning model, again, model is an algorithm, right? It has some steps in it.
yes.
Some steps I can do it in quantum machine. Only that context.
Okay.
Right? Okay, so that's it from my side. I think you got little ideas about quantum machine learning. If you want speed, if you're talking about security aspect, use quantum, or otherwise the basic machine learning or basic machines are sufficient for doing today's problem. Tomorrow we may get lot of data, we may get lot of challenges, we may need quantum. But for today 2025, if you ask me, only if you're looking for speed and security, you go for quantum. Otherwise, the basic quantum basic setup is enough for that. Okay, so I hope you enjoyed learning my session. Thanks for answering those queries at the beginning,
Sir, sir,
answering those
sir,
MCQ based questions.
sir,
I'm here
just a
for,
minute, sir.
please.
Sir, I'm Dr. Rangaro, sir, from Potticherry Engineering College, sir, Vijayawada.
Yeah.
Sir, since 2 decades, I am working on ECC, sir, elliptical cryptography, ECC.
Yes.
In that, very long back, we used that ECC concept in CDMA technology, wireless communication.
Yes.
Later on, we had used the same concept in LTE also, that is
That
4G.
is based.
And
Yes.
later also, so later we had used that in 5G new radios, sir, concept also we had used it. But
Yes.
now after going through your session, so I want to implement this quantum in IMT 2030, sir. That is 6G.
Yes.
So after having your class, listening to the class, now I got some research problems, sir, which has to
Yes.
be implemented in IMT 2020. Sir, regarding,
Good. I'm
thank
happy
you
for
very much,
that.
sir.
Yeah.
Yes, sir. Sir, thank you very much for your session, sir.
Yeah. Very happy for that. Thank you.
Yes, sir.
Thank you, sir. Nice session.
Sir, can we,
Please.
sir, can we implement by using MATLAB also?
For now, we don't have these libraries in that.
For the small application also, we can't do, sir.
Yeah, Python, it should be easy.
Okay. Okay, sir. Thank you.
Any other frameworks and tools, sir, rather than Python? Only Python, sir. Any frameworks or tools?
I am aware of only
IBM.
Python from IBM
Yeah.
Qiskit only. I am aware of that.
IBM Qiskit only, sir. Yes,
Yes.
sir. Google, sir. Google,
I think
Google
it's not giving.
CIRQ.
Yeah, it is there, but it's not too
CIRQ.
friendly. It is not that too much. It is not flexible to use. I think Amazon has one
Penny
thing.
Lane.
In Amazon,
Yeah, Penny Lane.
there is.
Penny
Yes.
Lane, I think. So.
Yes. In
Is
Amazon,
it
we have this.
error prone? Yes. Is it error prone, sir? This about errors here, sir. While
You're
working
telling
with the QML models.
No, nothing about
error?
we need not worry about error part here. Error correcting, error coding, that is not that problem is not there in this QML part.
QML. Okay. Thank you very much. So,
Sir,
can you share this notebook, sir?
I will share it. I will send it to Tirumala madam. Maybe madam can communicate it with you.
Thank you. Thank you so much.
Sir, is there any reference book to implement this quantum gates using this variational circuits, sir?
Yes. Again, we have some. I think IBM has one. This what we say. In Coursera, we have one course, and IBM videos are there. IBM has done some implementations. You can find in the internet. I will share. I think I will share some data with whatever I have with me.
Madam, sir.
Yes, definitely. I think you can post the questions in the chat box. That will be easy for me to read and quickly answer if you have any questions.
Sir, if machine learning works on classical data, if we apply this to quantum, how can we convert this data, sir?
Which data? Sorry, I didn't get you.
Sir, if we work on machine learning, sir, if for any data,
yes,
that will be classical data, sir.
Yes.
If we want to work with that same data with quantum computing, we have to work with qubits, no, sir?
That's what I have showed, no, in the demonstration. It will convert you have tried Python commands which will convert that quantum classical data into quantum data. Automatically it will do that.
Okay, sir. Okay, sir.
Yeah.
Thank you, sir.
Okay, thank you so much. I think uh,
I
Sir,
hope all the participants are enjoying this session, right? Today's session was truly informative and gave us a clear understanding about how the classical data is transformed into quantum format. One of the key insights highlights was the explanation of how classical information, which we usually represent zeros and ones, need to be encoded into qubits before it can be processed. The research person also explained how enabling quantum algorithms to process the data in parallel. Overall, the session gave us very good insights into various data encoding methods and how they form a foundation for quantum machine learning, quantum communication, and quantum information processing. The way these concepts were explained was very understandable. It was indeed highly informative and engaging session. Hope all get the correct information from the research person. Thank you, sir.
thank you so much, madam. I can leave, madam, now.